telematic confirms the flood event. So with these, then there are significant effort. Malawi government, the World Bank has noticed the significant impact that has made, and therefore is advancing some help to the authority to upscale this to the southern districts that are oftenly affected by the cyclones year in, year out, but also some significant effort in terms of mainstreaming the warning system to the community level understanding. Instead of giving the warning in terms of discharge, we put it in the level that the community understands in terms of the water level or the water height, or what we call known as the stage. But also more partnership is still needed in this particular area to deliver the much needed information that the vulnerable community needs, so that they can take action within themselves that may enable them, to take certain decisions that would save their life, but also save their property and also the livelihood. So through this, it's a collaborative work. It's not a single individual's work. It's a collaborative with different institutions coming in, leveraging on the strength and synergies of different institutions to deliver such a product. And in this particular case, we have other partners who participated in this, and it's just good to acknowledge them, including the Malawi government. Thank you so much.
Thank you, Calvin. So we are going to leave the questions to the end of the session. Our next speaker, Dr. Benson Kenduino, is a PhD in civil and environmental engineering with 2 years of postdoctoral research, and is currently a geospatial data scientist at the program, CERVIR program. He has over 11 years of experience offering spatial data-related solutions, including surveying, mapping, remote sensing, machine learning, crop modeling, and index insurance. Dr. Kenduino. Thank you.
Thank you very much. Good afternoon. I wish to spend some time to talk about the use of Earth observation to support development of design and evaluation of index insurance. And just to start, probably we are asking ourselves, why agriculture? So most of us know that, for instance, in Africa, by 2030, population will hit 2 million or probably more. By 2100, we are looking at 4.5. And of course, this is something that then what comes into mind is the demand for food will increase. We are also having the same challenge in Africa where, okay, it's back. Yeah, so climate change is also there. It's impacting us. And therefore, for instance, we see that there's a significant investment that is required in order to make sure that we fight hunger. And one of the tools that can help in terms of social protection is normally insurance. So, and in the context of agriculture, we are using index insurance. And index insurance is just, for instance, in this case, it's a proxy that we use some Earth observation-based index. It could be rainfall. It could be NDVI, for example, from a satellite, gross primary productivity, to sort of represent and capture production. And the advantage of this is that, for instance, when index insurance works, we are able to cut administrative costs. So imagine if you have a car, whenever you normally have an accident or something like that, you would take your car to an assessor or something like this. So in agriculture, you would need someone to go to the ground to verify the losses. But if you use Earth observation, you're cutting the cost of administration. The other thing is that its advantage is that it helps against cushion against moral hazard. That means no one is able to manipulate. For instance, if I'm a farmer and I know that the assessor is my cousin, I might kite away all my crops and say I suffered from a loss and I'm compensated. The other thing is that also you will not, I don't know, the slides are not stable. You'll not, yeah, they're back. So you'll not, for example, the insuring agencies will not suffer from whatever you call adverse selection. That means that you go somewhere, you want to insure people, and all people that you're insuring are all the ones that are facing risk. and therefore it pushes the cost of insurance higher. So going forward now to look at this in context is that when insurance works, one, it pushes the farmers to go all the way and invest. If you look at the diagram there are two scenarios. The upper scenario shows you when a farmer does not have insurance, what happens. So looking at Kenya, for example, consistently for the last 5 years, we've had challenges with rainfall, with this year being the worst. So if I'm a farmer, I might say, okay, last season was not so good. I'm not sure what will happen in this season. Let me use some just local seeds, get fertilizer to just get me by, and then do the planting. What this impact has is that the production will be low if indeed the rainfall comes. Okay, the other scenario is that if I'm cushioned and I'm an adverse farmer is someone who fears risk, then I know that someone has my back, then I would invest as I would normally do, get the certified seeds and fertilizer, and do everything that I can, because I know if there is a failure, if that index insurance really works, that someone is going to compensate. Therefore, this has called, because the seeds, for example, are regulated, they are certified, but in the index insurance is something that has come in, and there is need to evaluate and certify it to ensure that it works when it is needed. And the diagram to the right, depending on how, I think to the left as you are seated, shows, for example, the income when someone does not have insurance. You see the red line is that to the extreme, when you're protecting your assets without insurance, you fall on the shocks when they happen. No one is there to cushion you. But the insurance on the other side, the line going, for example, if you follow the blue dots, you'd see that if your cushions and the insurance is working, during the worst, the bad times of the world, you're covered. But what you would notice is that whoever is taking insurance, even in the good times, the line, they are always incurring income. That's why you see that, for instance, if you look at the next diagram, I hope it comes. Yeah, there. So if you look at the neediness of a household, that is a curved line, vis-a-vis the benefit of insurance. There's always, the benefit of insurance will always be lower than the neediness of a household, because the household is paying premium. But what the insurance should do, it should provide a flow when it is needed. But when it doesn't work, then farmers are not able to invest. So I would go through, having covered just, okay, I think it went. So we looked at a case. In this case, it was an data that we had from the IBLI program, Index-Based Livestock Insurance. And we developed several models to be able to predict mortality. In this case, we had linear regression, we had segmented regression using different linear and segmented regression itself. And you can see from the left diagram, for instance, whatever people use to measure as a metric, if you're trying to predict yields or mortality, in this case for livestock, most out there, mostly people use either RMSE or R-squared. And then if you have a higher R-squared, you're happy that your model is able to capture whatever event you're trying to predict. Then to the right, you can see we have one of the tools that we have developed called the relative insurance benefit, which considers a simple economic framework of welfare. And what do I mean by this? We mean by checking, we are able to assess using economic principles to see, given different events, and in this case, events that are occurring, by monitoring them during the worst states of the world, does the insurance give benefit to the farmer? And I'll give you an example. If I have $10 million today and you gave me $10, it might not make an impact in my life. But during the worst times, when I have lost everything and everything, probably I have $100 to my name, and you gave me the same $10, it would make a difference. So this is what we are trying to assess here. We are looking at a metric that would help to evaluate insurance. And this is just a list of, for example, the Earth observation data that is available from charts, soil moisture products, precipitation and vegetative measures, and the satellites that we have are available to us to use. In the previous example, that the case study that we did here, we compared rainfall, some MODIS product and some MODIS products to do the evaluation. So therefore, I want to give here an example of, what happens in reality when when you have an insurance. So in this case, you have, we're talking about an individual who is insured, and for example, in this case, drought has occurred, they have lost livestock. For example, the IBLI program is currently using some MODIS product to do prediction, and it has moved from a reactive program to an asset protection measure, where if you look ahead and we think that the situations will not be good, we make a payout, and the farmers are able to buy medicine or fodder to protect themselves. So in this case, you can see that in this particular design, there were cases where we had the false negatives and the false positives. So the false positive is where you get a payment even if you don't deserve. So someone who has insurance will be happy, oh, I got some money. But remember, in insurance, you give out $1 at a cost of, let's say if the premium is 20%, is you pay for $1.20 for $1. So when you are paid back, when you don't deserve it, it means that the premiums would go up next time. So it doesn't help, all right? So the other thing is, the worst case scenario is that when this farmer needs us to pay them and we are not paying them, then it's also a challenge, because then the farmer is not cushioned. So by looking at this, for example, diagram, we are able to advise, because the idea behind the evaluation is to be able to advise on the program design to make sure that the design actually helps the farmer, and on the other hand, the insurer is not making payouts when they don't deserve, so that both the welfare is taken care of across board. I would go here, and you have two diagrams, the one on the left and the one on the right. The one on the left had a higher R squared, which means that by our eyes, when we do, when you're building a model to do yield prediction or whatever, in this case, mortality, then you would think that it is accurate enough. But you see that the diagram on the right, which has a higher insurance benefit, was able to capture the worst, the bad states of the world. That is on the diagonal side, the northeastern part. Those are the people we care of. We don't care whether the model is doing well capturing the low mortalities. When the mortality is low, it doesn't matter. No one is losing anything. But when mortalities are higher, that is when we need to capture it. So this is just another example. And these are some of the programs that are going on. Some of them are in Kenya, like the index-based livestock insurance that we are working closely together. There is the Kenya Livestock Insurance Program. We have there's another one for crop cuts in the ministry. There are tons of them. You can refer to those papers and look through them. So this product, the tool that we developed, is available in R as an R package. We have also built a case study. If you go to the website, you can go step by step and see how you can use Earth observation to design a program. And as you're doing that, you're making sure that this program makes sense. That is, that when you launch the insurance program, it is able to meet the welfare of the farmers and the insurers. What do I mean by that? That the farmer is cushioned when they need it, and that the insurer does not make payouts when they don't need it, because that will push the premiums up. And in the end, the insurance will not be sustainable. So I would like to end my presentation because my time is up, and I leave my slide on acknowledgement. Thank you.
Thank you so much. Our next presenter is Madam Kalaletsang Kevine. She is a junior data scientist at the South African Environmental Observation Network, SION. Her expertise is in GIS and remote sensing. Her research interests lie in Earth observations and environmental sustainability, with particular interest in biodiversity conservation and terrestrial ecology, focusing on the application of GIS and remote sensing methods within this research. She is currently working on the South African Risk and Vulnerability Atlas, SARVA project, an initiative of the South African Department of Science and Innovation led by SION. Madame Kevine.
Thank you for that introduction. Technical check. Okay. Oh, it's going to the front. I needed to go back. Wait. Okay. Good afternoon, everybody. As per presentation, my name is Kalaletsang Kevine. I'm from the South African Environmental Observation Network. My presentation today is titled The South African Risk and Vulnerability Atlas, an open access data platform. Basically outlined, the first slide is just an outline of my presentation. And then let's get started. So the world is facing a number of complex global challenges, which include but are not limited to climate change, urbanization, the rise of pandemics and epidemics. These increase the susceptibility of communities to natural and anthropogenic disaster risks. So WMO recently reported that globally, climate-related disasters have cost us approximately $3.6 trillion in economic damages, as well as the loss of more than 2 million lives over the past 5 years. Within that same time period, WMO further reported that 1,695 of these disasters were recorded in Africa, which cost us the loss of more than 700,000 lives, which approximates to 36% of the total, as well as 38.5 billion in economic damages, which is 1% of the total cost. So therefore, it is generating an enabling environment for communities, government, and sectors to respond to global challenges is critical to ensure future resilience. And in so doing, this will promote the ability to profile, track, as well as monitor the vulnerability of communities while providing insight into their respective socioeconomic dynamics and challenges, as well as contribute to the ability to timelessly and proactively address potential risks associated with global change. So the South African Environmental Observation Network, commonly referred to as SION, is a long-term environmental observation and research facility of the National Research Foundation, funded through the South Africa's Department of Science and Innovation. We are dedicated to long-term in situ global change observation research, and our vision is to provide world-class environment research platforms for sustainable society. We have 7 nodes which are distributed across both the marine and terrestrial environments of the country, as well as 3 research infrastructures. Our focus areas are environmental observation, data management, and education outreach. Therefore, we've got a diverse array of sites, instruments, and infrastructures, models, as well as staff distributed across both marine and terrestrial environments, supporting well over 100 researchers and students a year. We provide detailed in situ data for users' inputs to models, model parameterization, improved process representation in models. Okay, so with our focus areas being data management, earth observation, and education outreach, the South African Risk and Vulnerability Atlas is now managed by us. It was initiated in 2008, and it's commonly referred to as SARVA. It is an open access platform that unites data to solve complex interconnected problems. It is mandated by the Department of Science and Innovation to preserve and provide access to global risk data for South Africa. During conceptualization, this is the framework that was used for SAVA. We stated that risk refers to the likelihood of an adverse impact from an event, and they are a result of an interactions of vulnerabilities, exposures, and hazards. SAVA has three core principles, which are first, accessibility, as to provide access to scientific data and observation of long-term environmental, societal, as well as economic trends. Our second core principle is usability, is to make sure that the data that we provide translates into actionable and impactful information. And third, but not finally, is responsiveness, to ensure that the data and information is based on evolving user needs and changing global challenges or socioeconomic dynamics. So SAVA is built on the open data architecture. SAVA open data architecture is based on the infrastructure of the open data management system supported by SAON. The open data management system allows for the publication, discovery, dissemination, visualization, as well as the preservation of data. It is based on the FAIR principles, and it has standardized metadata within the catalog. The open data platform offers the ability to store metadata and data sets, integrates management of and access to a variety of data types, including spatial and time series data, digital content, multidimensional, as well as modal data. And it hosts several data portals, including SAVA and SAON's very own open data repository. This is just an example of the open data repository that you guys can visit. And then the objectives of SAVA, which I've been speaking about, are to profile the vulnerability of local municipalities, as well as proactively strengthen the ability of the people of South Africa to cope with the range of natural and anthropogenic hazards. The second one is it aims to equip decision makers across the board, being it community sectors as well as government, with spatial and non-spatial data on impact and risks associated with global change. And yeah, let me just, and then finally, and then we want to promote access to data, which will ultimately place policy and decision makers in a better position to inform effective response measures. And then the information which we provide is decision-ready data, which is translated into digestible narratives, which range from dashboards, infographics, as well as a searchable atlas. Yes. So in there, with that being said, SAVA was designed and reinvested front-end platform with data dashboards and interactive visualizations. It is an online catalog which currently hosts more than 3,000 data sets. It has online atlases on climate risk, disaster, air quality, commercial agriculture, as well as environmental vulnerability. It has interactive dashboards, which includes currently a beta version of an economic dashboard. And we have managed to link at least 15 out of the 17 sustainable development goals to district and local level. So the data hosted on SAVA is downloadable, and it is quality assured and quality controlled. These are examples of some of the data which one can find on SAVA. We focus on data access for SAVA 3.0. So therefore, we want to provide decision makers with material that they can use to assess municipalities in managing risks, in managing the risk associated with global change. And then global change resources hosted on SAVA include scientific data and long-term observations, static content, reference to documentation, and reports and other digital objects. Below there is a picture showing that we currently have close to 2,000 open spatial data sets, 3 risk profilers, 53 vulnerability indicators, as well as 49 SDG indicators linked to data. And then SAVA was designed with the following users in mind. We've got first the decision makers who require the information for reporting and planning. Then we've got the domain experts who require the data for the development of sector-based atlases. Then we've got the research community who require the data for specific studies. And then finally, we've got the fourth user who are the technical teams who develop apps based on the data that's hosted on Sava. So the Sava SDG dashboard tool serves as decision support tool for municipal planners to gather data on where their municipalities stand with regard to sustainable development goals. The indicator data sets which are available on Sava are presented at the highest spatial and temporal resolutions possibly. We always aim to have the data at local municipal level. And then due to this, there's always new data is constantly being added to Sava. So this is an example of our SDG page on the Sava website. These icons are interactive. So one just clicks on the icon of interest, and then it would lead you to Sayon's open data catalog, which shows you the number of data sets that we have quality assured and quality control, which are within the repository. For SDG 15, as stated there above, we've got 395, and then one can further filter these based on the filters to the right. And then my final example is the environmental risk and vulnerability profiler that was created. This linked the local municipalities' environmental threat status, protection level, endemism, as well as year 2 collapse. So this screenshot was captured with the endemism layer active. What it just shows you is the nativeness of the species within the environment for the local municipalities. And then further down, this can also be used to show you the years of collapse, which is the risks of the ecosystems depleting, as well as the vulnerability, which is the threat status. How vulnerable and sensitive are those ecosystems to hazards which they face, as well as the protection level, how well is it protected thus far within the South African context, as well as the nativeness. With that being said, I'd like to thank the following organization: the Department of Science and Innovation for the funds, the South African Risk and Vulnerability Atlas team, as well as NRF Sayon. Thank you.
Excellent presentation, and thank you so much. So please, I hope that you are all taking notes so that we can ask questions at the end of the session. Our next presenter is Mr. Kudus Taiwo. He is the Deputy Director at the National Center for Remote Sensing in Jos, with over 2 decades of working experience in space technology research and development. He's currently the head of the Department of the Satellite Ground Receiving Station of the National Center for Remote Sensing, with the responsibility of acquiring medium resolution real-time satellite images from space, covering 1/3 of Africa's continent. He has been involved in national projects in Nigeria related to land use, land cover, assessment of deforestation of forest reserves, mapping and database creation for mineral deposits, and many others. Mr. Taiwo. Not here? Okay. So let's go to Mr. Catherine, and let me introduce you. Madame Catherine Nabukulu is a 2nd-year PhD candidate with an academic background in geoinformation science and Earth observation. Her research focuses on understanding the spatial and temporal variability of rainfall accompanying tropical cyclones for a reliable integration and flood hazards assessment. She holds a Master's of Science in Geoinformation Science and Earth observation, and she specialized in natural hazards and disaster risk reduction from the ITC University of Twente. Catherine?
Thank you, Angelica, for the introduction. She didn't mention that I'm from Uganda in East Africa. And I am really humbled to stand on this platform to tell you about the research I'm doing for my PhD. We are in the early stages because I recently completed the first year, and yes, I'm in the second year. And we also sent out our very first paper, which is currently under review. So I would like us to know what I am doing, and I'm also looking to collaborate with different people because my initial focus area is in the Caribbean, but this is very much applicable to Africa because tropical cyclones impact the eastern coast of Africa. I also have some of my colleagues from ITC. They are seated right there. Thank you for attending the presentation. All right, so what are we doing? We are utilizing satellite precipitation estimates to derive tropical cyclone associate rainfall signatures, and we are focusing towards improved flood hazard assessment. So I'll take you through why we are doing the research, the experiments I've done an experiment for Madagascar, the conclusion we've made thus far, and also how we expect to proceed further in this research. So you probably have heard about hurricanes, cyclones, typhoons, and when we talk about all of these terms, we are referring to the same system. We are talking about tropical cyclones, and these systems form around the tropical equator. They are associated with very strong winds and heavy precipitation. And for a tropical cyclone to form, you need existence of warm, moist air conditions over the open oceans. And now with climate change, as the oceans become warmer, there is persistence of favorable conditions for tropical cyclones to form, to grow bigger, and even move very fast. And as these systems move over the open oceans, they interact with land masses and have always brought devastation over highly populated coastal areas and as well as islands. So the image on the top right highlights some of the African countries in the Southern Hemisphere that are usually impacted by tropical cyclones. And at the bottom there is an image over Madagascar due to flooding devastation in one of the tropical cyclone seasons. So these systems are not going away, and they are associated with a seasonal occurrence. So affected areas always suffer annually.